Well, are they? I mean, actually observe them and see if you think the tablets are about the same size or if the bubbling is about the same amount. And then if you kind of look, I mean, I think these are cloudy and bubbly. This guy is not nearly as cloudy compared to most concentrated vanillas. Let's see if you can see a difference. Can you see a difference in the thickness of the tablet? Yes, definitely. I don't think that any of these tablets are actually going to dissolve all the way gone in the length of this class period. But, so, try to get some of the bubbles to go away so you can actually see in there. So these three are the same concentration. Do they look the same rate of dissolving? It's the same amount of each tablet gone. And then these three, it's like more, less, and very less. If you think of the rate, if you stand up, you can see this one is not as cloudy as these, but more cloudy than that, more bubbly over here, Oh, I'm gonna have a lesson in today. We talked about that in physics today. Everything stops and other things keep going. Okay, so you guys can keep observing while I don't see that. Now we'll talk about writing a discussion. So here are the kind of important points to talk about in your discussion. So if you finish your observations, I'll give you a minute before still writing and such. Yeah, again, instead of 1 cup. Yeah, because that's all that's there. There's no water. I put 50 vinegar, 50 water.
Oh, 50 water, okay.
So it's all three of those are 100 total.
Oh, great.
Yeah, I'll write that. I don't know if I can fit that. So what they contain. Okay, that's what each contains. Clay, if you want to come that instead of the cups we used at graduated cylinders and milliliters. Okay, so you can work on your observations later. Let's try to move on to the discussion, and then we'll come back and see how things are progressing in a few minutes. So the first thing you really want to talk about on the back page here for your discussion, which of those beakers have the same concentration? The first three. So I even numbered mine 1, 2, 3, 4, 5, 6. So I could just say in my discussion, beakers 1, 2, and 3 have the same concentration of vinegar. No water was added. It's just the same vinegar straight out of the bottle. But they have different amounts. Right? So concentration is controlled by speed. So the same concentration has the same speed. so we predict they have the same speed. Do they actually? What did you observe? So let's try to reach a consensus. Did the first three beakers have the same rate? Or did the amount of vinegar play a role in how fast they reacted? So, if you look at the bottom, what do you actually see? Do you see a difference? You think this one's smaller? Okay, so important part of science is to actually write down what happens instead of what you think should happen. So what do we see? Because I definitely see a difference. Jenna sees a difference. I see that even though these have the same concentration, it looks to me like the one with a larger amount of vinegar has a faster reaction. More of that tablet is dissolved in this one, which has, can you see how this one's thinner? So, then we can think about why that is, and we might have to do more experiments to test that out. Well, instead of saying more, with 50 milliliters of vinegar, and you could even say, which was not expected. So does this mean that science for the last thousands of years has been wrong and that concentration isn't the only thing that affects rate of reaction? No. Okay, so when you're taking your test, when you're considering these things, concentration is what's important and it is what affects the rate of reaction. For us, I think we're seeing this little difference not because the concentrations are different or not because there are other factors that actually do affect rate, but we're seeing it because this used up the vinegar so quickly that the concentration of unused vinegar quickly got small. So the reaction started at the same rate, but it finished at a different rate. And that's kind of complicated, and so you don't have to try to explain, you can just write your observations. So I'm telling you it truly should have been the same rate, but as a reaction goes along, chemicals get used up, that concentration diminishes, and that happened much more quickly in the beaker with a smaller amount. I think next year I will use cups instead of milliliters, and maybe that won't happen. So, then we're going to compare cup 1 and cup 4. So the next part of the discussion, cup 1 and cup 4 had the same amount of vinegar. Why do we see such a difference in their rate? So we put 50 milliliters of vinegar in this and 50 milliliters of vinegar in this, the same amount. But we also put 50 milliliters of water in this one. So this one is more dilute. So why do we see? So look, this one is nearly gone. That one is still quite thick, right? Our concentrated vinegar is nearly gone. Our diluted vinegar pretty thick. So if it has the same amount of vinegar, why do we see such a difference? Nearly gone, pretty thick. Nearly gone, pretty thick. Why do we see a difference? Okay, Joshua.
And we see a difference because since the fourth beaker had water in it, it slightly diluted and the concentration became slower.
Okay.
It slowed down the concentration process because of the water.
So beaker 1 had a faster rate than beaker 4 because what Joshua just said. Because beaker 1 was concentrated, beaker 4 was dilute. probably you can give us more elegant wording than that. But, so, even though they had the same amount of vinegar, the concentration was different. Even though both maybe vinegar went at a faster rate than beef before because more concentrated vinegar reacted faster. Even though both had 50 milliliters of vinegar, because beaker 4 had water. Okay, I wedged the H2O in there. Let's see. Can anyone think of anything else that we might want to mention in our lab report, in our discussion section? There's one really important thing that every lab discussion should have, right?
I should know this, I'm not sure.
Oh, come on, I dropped 2 Tums into one beaker, I spilled all over the table.
Oh, yes. Air.
Error, discuss the sources of error. Okay, so what kind of, other than those things, what kind of sources of error might we have?
Bad measurements.
Bad measurements, I was definitely eyeballing those guys, but, yeah, I mean, that could happen. I didn't measure super carefully there, Chris.
They weren't all dropped in at the same time, the Tums.
Okay, so there were definitely a few seconds from here to there, but me dropping 2 into one, fishing it out, and putting in the other is definitely an even bigger source of error. So sources of error include is a good way to phrase that because you might not think of all of them. There's always lots of them.
Is there a Josh in here? Is there someone named Josh? You're the source of error for every experiment. That's how it always goes in science class. There's a person named Josh. They're always the source of error. Sorry.
He's not a Josh.
It's not Josh. You Joshua?
He is Josh. His brother's Micah.
Oh.
I called Micah Josh this morning, and so I've been awful about their names all day.
Sorry, that's just how it works in science class.
Dropping 2 Tums into one beaker. I don't think there's a Josh in my chemistry class. That's
There
like
was
a
last
first.
year. Yeah, there's none in physics this year.
Huh. Source of error includes dropping 2 Tums into one beaker. The other one is I did spill. When I was swirling the beakers to stir, a little bit sloshed out at least once. Definitely bad measurement. But there's one other really big source of error. How are we judging how much of the tablet is consumed? All right. What's he do? How do we decide? What? How do we decide which one had the most of the tablet used up? Stop. Jesse, what do you think? How are we deciding? Patrick? How are we deciding how much tablet got used up?
Maybe the water we put in the concentration.
Yeah. Joshua?
To just observing it.
Okay, so we're just eyeballing this. So we're not actually taking those tablets out and seeing for real which one, lost the most mass. Maybe they were all different sizes. I don't think there's any stipulation that they all have to be exactly the same size to start. We're not measuring how much they weigh at the end. We're just looking with our eyes and making a judgment call. And that is not a very precise way to do science. think it works just fine for our purposes today, that we can kind of see that more concentrated solution used up more tablet, and it's much smaller than this much, oh, I spelled everywhere again, much less concentrated, it's very thick still. But it definitely does, if we really wanted to tell the difference, say, between this and this, I think we'd have to take them out and measure their mass, and we'd have had to measure their mass at the beginning to see how much they changed. So those are sources of error. And it's always good to think about that in the lab. Think about how you're not doing things as well as you could, how you're making mistakes, and to record that, because that can always make a difference. You can come up with better methods of doing things. So that would be your whole discussion, basically. And the last part of your lab report is going to be a conclusion, which is definitely not going to fit on the board. It should come after the discussion and on that back page, but I'm going to wedge it right here just because I'm out of board space. So when you write a conclusion for a lab report, you always want to refer right back to your objective. So if my objective is to count the number of Tums in this bottle, then my conclusion would be what?
There are this amount of Tums.
Exactly. There are, maybe it tells me, it doesn't. There are 150 Tums in this bottle, if that is in fact how many Tums are in the
It's
bottle.
149.
So your objective and your conclusion are tied together. So if my objective was to observe the effect of concentration on a chemical reaction, well, what did I observe? What's kind of a general principle for how concentration affects rate? Somebody who hasn't done a lot of talking. Lily, what do you think is a good general principle for how?
General principle,
Yeah. How did concentration affect rate?
concentration by rate. Well, the more concentration, the faster the tub dissolved, and the less concentration, the slower it dissolves.
Okay, so more concentrated vinegar dissolved the Tums faster than diluted or less concentrated vinegar. Something like that would be a great conclusion. It goes right back to your objective to observe concentration. That tells us what we observed, that the ones in concentrated vinegar dissolve faster than the ones in less concentrated vinegar. And that's a good general statement about that. That's perfect. Now, how much time? We start, what, 12:20? This is now 1:30. So I'm probably right at the point where class should technically end. So you guys are going to go home. You're going to do the first half of Module 2. So what that's going to look like is you open up to Module 2, which starts somewhere like page 25, and you work through until you get to On Your Own 2.5. So that 2.5 and 2.6 are actually in the same box in this case, so you're really going to go to On Your Own 2.6. Don't even get up. Not bad. I still get like 10 more minutes. So you're going to start on page 25, read to page 36. You're going to do On Your Own 1 through 6 this week. You should write this down. On Your Own 1 through 6. Usually you stop at 5, but since 6 is in the same box, you should just do it. And then if you look at your study guide, when you get through 2.6, the next thing you're going to read that you will not read this week is global warming, which you are welcome to disagree with Dr. Weil about, and that's fine. If you can support your answer, I won't mark you wrong just because you don't say the same thing that Dr. Weil says, because that is a controversial topic, and there are scientists and data on both sides of that. So feel free to think about that topic yourself. Let's see. So if we look at the study guide, we would probably find, where do we, probably carbon dioxide, greenhouse gases, exhaling stuff. So you're gonna do study guide 1 to 12, it looks like to me. Study guide 1 through 12. And then if you look in the back of your book, there's the summary. And we're stopping at global warming, so I would say either 6 or 7, and I'm not entirely sure. So summary 1 to 6, maybe 1 to 7. Summary 1 through 6. That's what you're gonna do this week. You're also gonna take the test for module 1, because we finished module 1 today. So make sure you study. If you struggled with the little quiz at the beginning of class, and you really extra wanna study, you can finish this summary here, go over these problems with the answer key and your mom if you are struggling with unit conversions, for example, and that'll work just fine. Maybe we'll zoom through the end of the summary with that last 5 minutes I've got. So take out your module 1 summaries, and I'm going to sit down. Clay, if you want to film, I don't know, in some way that doesn't, that's my 5 minutes. Let's see how fast we can read.
What do you want me to film?
Anywhere that, like, just film each person who gets to talk, I guess. Okay. So don't worry if you don't know everything right now. We're just reviewing for the test. So I'm going to start with Lily, and we'll just go around. So atoms are the blank unit of matter.
Atoms are a chemical unit of matter.
Mm-hmm. Or you could say smallest.
Small chemical.
Any of that would be great. They are so blank you cannot see them.
We keep on.
Yeah, you go ahead and read.
They are so small that you cannot see them. Images of atoms produced by scanning tunneling electron microscopes are not pictures, but are the result of a computer calculation. Such images are part of a large amount of indirect evidence that indicates atoms exist. When 2 or more atoms link together, they form a molecule, which has its own unique properties.
Excellent. Anna? When a substance is made of billions and billions of the same atom, it's called an element. While substances made up of billions and billions of the same molecule are called
Compound.
some substances called
Mixtures?
are made of more than one kind of atom or molecule. So if you mix, like the air we're breathing right now is a mixture. It has oxygen gas and nitrogen gas, traces of other sorts of gas, carbon dioxide, for example. And so it's a mixture. Let's see, where are we? In experiment 1.1, which we didn't do yet, we'll do that in a couple weeks, you watch the molecule known as water break down into 2 elements. What's water made of?
Hydrogen and oxygen.
Good. In addition, you saw the blank in the wire, an element. Well, you didn't see that. But probably the wire would be made of copper?
Yeah.
Okay. And the wire, which is an element, copper is an element, react with the baking soda molecules to make copper hydroxycarbonate. And we might actually not use baking soda when we do it, because that's not really the best way to do things when you do this experiment. So you'll kind of see. I'll decide what we're going to use. I might use Epsom salts, which are, magnesium sulfate maybe. And it doesn't have that side reaction. It has a different side reaction, which is not as pesky. So Patrick, when making measurements, the blank we report are just as important as the numbers. Units. When you take this test, you must put a unit with every numerical answer. And forevermore, please. The base metric unit for mass is the
Gram.
when the English unit for mass is the
Slug.
base metric unit for weight is the
Newton.
and the base English unit for weight.
Pound.
Although the weight of an object varies depending on gravity, it's what does not?
Mass.
Mass. So here on Earth, your mass is the same as it would be if you went to the moon, unless you ate or chopped up a finger. But if you measure your weight on Earth and then on the moon, it would be different because gravity is different on the moon. Let's see. 404. Don't panic, Jesse. The base metric unit for length is the,
Meter.
yeah, and not the cubit for sure. And the base English unit for length is the foot, inch, something like that. The base metric unit for volume is the, what do I measure in for volume? Yeah, my base unit, but this is in 50 milliliters, but the base unit instead of milliliters would be upper
Liters.
liters. Base volume unit is liters. And where am I? The English unit for volume is the
Gallon.
sure gallon, liters, or I mean not liters, quart maybe is gallon the base unit. I don't even know that. In the metric system, prefixes govern the length of a unit.
Space.
There it is. The base of a unit. Size, magnitude. What do you all have?
What's size?
Size. The milli prefix means 1/1000. Yeah, like either 0.001 or 1 divided by 1,000. While the prefix, what prefix means 0.01? Centid means 1/100th or a 1 in the 100th place. The kilo prefix means 1,000. And so an object with a mass of 1 centigram has a smaller or larger mass than a mass of 1 kilogram. Smaller. A centigram is little, kilogram is bigger. The metric unit for temperature is degrees.
Celsius.
Celsius. This unit uses no prefixes. Oh, so you don't say like centa Celsius or something. That doesn't happen. In this system, water freezes at
0 degrees.
and boils at.
100 degrees.
And if you ask anyone in my chemistry class, they promise you that that is really true because they spent like an hour and a half today. In the Old Testament, the unit, Ryan, for length was what we used last week with strings. Cubits. And concentration. We really talked a lot about that today, so I guess I'll let you all go. If you can help me tear down the classroom, if your mother is not waiting.